Welcome to this explainer. Today, we're getting right into the absolute magic and the extreme engineering of how autonomous vehicles actually perceive the world. We're going straight under the hood of the spatial AI perception engines powering self-driving cars. And specifically, we're looking at the dueling philosophies of Waymo and Tesla, because it's wild how two of the biggest companies on the planet are taking completely opposite approaches to solving the exact same problem. Let's dive in.
So here's our roadmap for today's deep dive. First, we'll look at the sensor divide. Then we'll break down Tesla's vision and voxels, followed by Waymo's 4D sensor fusion. After that, we're diving into the end-to-end revolution. And finally, we'll wrap up with HD maps versus generalization.
All right, part one, the sensor divide. Two opposite approaches to solving the exact same physical problem.
Now, the sheer physical contrast between these two vehicles is just staggering. On one side of the industry, you've got Waymo. A Waymo vehicle operates on this massively redundant, multi-modal stack. We're talking 29 cameras, 5 LiDARs, and that includes a roof-mounted mechanical long-range LiDAR, plus 4 solid-state short-range side and front LiDARs, known as the Laser Bear Honeycomb. Oh, and let's not forget the proprietary imaging radars. Honestly, it's basically a futuristic robot covered in spinning lasers. But then, on the flip side, you have Tesla. Tesla's Tesla Vision stack completely rejects LiDAR and radar. Just completely throws them out. They've stripped away the hardware to rely entirely on just 8 cameras. That's it. It's a massive hardware divide right out of the gate.
Moving on to part 2, Tesla's vision and voxels. We're looking at reconstructing 3D reality from flat 2D pixels. Okay, so to understand why Tesla completely overhauled its software for a camera-only setup, we really have to talk about this fascinating concept called ontology cracks. Basically, what happens when an AI sees something completely new. See, traditional object detection draws these fixed bounding boxes around known categories, right? Things it knows, like cars, trucks, and pedestrians. But what if a Tesla comes across an overturned truck that's spilling its cargo all over the highway, or some totally weird, unique construction barrier? Well, if that novel object wasn't perfectly mapped out in the AI's training data, standard classifiers might literally just ignore it, just pretend it's not there. That massive blind spot? That's an ontology crack. And at highway speeds, that is an absolutely critical safety failure.
So, here is the crucial point. Tesla's occupancy networks solve this problem by just completely changing the question the AI is asking. Instead of the AI racking its virtual brain trying to figure out, hey, what exactly is this object, the system simply asks, is this space occupied? Tesla introduced this back at AI Day 2022, and this algorithm literally divides the 3D space around the car into volumetric pixels called voxels. It's actually really helpful to think of them like invisible Minecraft blocks just hovering over the road. The system simply predicts the probability of whether each voxel is occupied or free. By bypassing the whole classification thing entirely for safety, it forces the car to stop or swerve for any physical obstacle, whether it knows what it is or not.
And here is the exact step-by-step pipeline Tesla uses to replicate a LiDAR point cloud using literally nothing but cameras and time. Step 1, it ingests raw 2D pixel feeds from those 8 cameras. Step 2, it uses some intense math to project those flat pixels into a unified bird's-eye view. Step 3, it generates that 3D voxel grid we were just talking about to locate the obstacles in depth. And finally, step 4, it applies something called 4D flow. This is where the network tracks these voxels across time, allowing the vehicle to predict exactly how moving objects like other cars or, a cyclist will shift their occupied space a few seconds into the future. Pretty wild, right?
All right, on to part 3, Waymo's 4D sensor fusion and the sheer power of multi-modal redundancy.
Waymo takes a completely different philosophy. By layering these very specific sensors, Waymo guarantees that if one system fails, another one immediately covers for it. Cameras are amazing, sure, but they get blinded easily, right? Direct sun glare, a downpour of rain, dirt, pitch black darkness. That's exactly why Waymo uses cameras purely for semantic data, things like reading a detour sign or checking a traffic light. Then, you've got the roof-mounted LiDAR shooting millions of laser beams a second to build a millimeter-accurate 3D point cloud up to 300 meters away. Then you add solid-state LiDAR to cover the close-range blind spots. And when the weather gets truly terrible, they use proprietary imaging radars that can perfectly track the speed and trajectory of objects through heavy fog, snow, or literally total darkness. They even have specialized physical wipers and cleaning nozzles just to keep this entire sensor stack absolutely pristine.
But here's the thing, Waymo doesn't just awkwardly bolt these sensors together on the roof. They weave all this data together at a really deep feature level using a system called 4D Net. Think of it as a deep neural network architecture that perfectly balances spatial resolution with time steps. It fuses the direct, physics-backed depth measurements of LiDAR, which, by the way, do not rely on machine learning guesses, they are hard measurements, with the rich semantic colors of high-resolution cameras into one single unified view. That right there is what gives Waymo such extreme spatial reliability, allowing their cars to accurately track something like a pedestrian from up to 500 meters away.
So, okay, we've seen how they perceive the world. But the next logical question we really need to answer is, how on earth do they process all of this massive data to actually make the decision to turn the steering wheel? Which brings us to part 4, the end-to-end revolution, abandoning C++ code for transformers. As it turns out, trying to codify unspoken human social rules like nudging your way into a tight lane, yielding politely to a pedestrian, or just surviving a chaotic highway merge using thousands of handwritten rules is virtually impossible. That realization forced an incredible shift in the industry. The old way was super modular. You had a perception layer, a prediction layer, and a planner all held together by thousands of lines of C++ code saying things like, if pedestrian is less than 5 meters away, hit the brake. But that code just became bloated with endless edge cases. It caused jerky driving, sudden phantom braking, system freezes. It was a complete mess. So the new way abandons all of that entirely for end-to-end neural networks. Now they just ingest the raw sensor data and directly output the steering, speed, and braking commands by essentially imitating human driving.
Now, the huge takeaway here is that the exact same underlying transformer technology that powers tools like ChatGPT is now driving our cars. Tesla's FSD version 12 literally scrapped hundreds of thousands of lines of C++ code to become an imitation engine, which learned to drive by training on millions of video clips of highly skilled human drivers. And Waymo is pushing the exact same boundaries. They're researching IMMA, which is a multi-modal neural network built on top of Google's Gemini, designed to map those raw sensor feeds straight into trajectory points. Both companies are heavily leaning into generative transformers and consistency models, like the S4 driver, which predict the joint trajectories of not just the self-driving car, but all the surrounding vehicles. This enables smooth, proactive yielding instead of that clunky robotic reactive braking we used to see.
And finally, part 5, HD maps versus generalization, the final frontier of autonomous scaling.
This right here is where we hit their most profound philosophical divide, how these vehicles actually understand their place in the world. The trade-off is stark. Look at Waymo. They rely heavily on HD maps. Before Waymo can operate in a new city, they have to painstakingly pre-scan every single street to create these centimeter-accurate 3D maps that detail every curb height and traffic signal. So Waymo gets extreme precision by comparing its real-time LiDAR against this pre-mapped virtual twin with almost zero drift. But it is incredibly expensive and slow to scale city by city. And if a sudden construction zone alters the road, the system can really struggle. Now, on the flip side, look at Tesla. They rely purely on generalization. Tesla completely rejects HD maps, basically arguing they're just too expensive to maintain globally. Their vehicles have to perceive lanes, speed limits, and complex intersections entirely on the fly using vision. Now, that is infinitely scalable to literally any road in the world instantly, but man, it places a massive, massive burden of absolute accuracy entirely on their software.
So as we wrap up this explainer, I really want to leave you with a final thought to consider regarding the future of transportation. We are basically watching two radically different engineering paradigms race head-to-head toward the exact same goal. So what do you think? Will the future belong to the robust, physics-backed safety of Waymo's multimodal sensor fusion and HD maps? Or will the elegant, infinite scalability of Tesla's vision-only AI ultimately be the key that unlocks the world's roads? Whichever philosophy ultimately wins, that answer is going to define the next century of how humanity moves.